On Friday, we took a look at an F versus T graph. I'm going to draw one with kind of a funny shape here. I told you I'd ask you this question on Friday. What are the three words that come to mind when you see this graph? Area equals impulse. Doesn't matter what you're asked. In fact, you aren't even asked anything yet. You still need to think area equals impulse. Now, a couple of questions about the area of this graph, the area that equals the impulse. This area right here is above the x-axis. What's different about this area above the x-axis versus this area down here that's below the x-axis? Over? Good. The stuff below would be considered a negative value, and the stuff above would be considered a positive value. Good. Now, we've got kind of a funny shape up top, and for that matter, a funny shape down below. How are we going to find the area of this crazy-looking shape above the x-axis? Oliver? Yeah, let's break that up into a triangle. We'll call it section 1. A rectangle, we'll call it section 2. And a triangle, we'll call it section 3. Let's get the area of all three of those. Let's consider them to be positive values. And then let's break the bottom one up into a triangle and a rectangle. Let's consider those to be negative values. Then we're going to add them all up, right? What is the area of a rectangle? Seems like a pretty simple question, but how do we find the area of a rectangle? Base times height or length times width, sure. And how do we find the area of a triangle? 1/2 base times height. Does it have to be a right angle triangle? They are in this case, right? But does it have to be a right angle triangle to use 1/2 base times height? No. Any triangle, as long as you have the base and the height, you should be good. All right? What if we're asked to go a step further? What if we're given the mass here as well? Let's say the mass is 100 grams or whatever. And we're asked to find the change in velocity of the object experiencing the motion in this graph. What if we're asked to find delta V? What are we going to do with that? We still want to think area equals impulse, right? So we get the area, that equals the impulse. Once we have the impulse, what do we do with it? Yeah, we divide it by 0.1. Good. In other words, we're going to set it equal to m times delta V, m times the change in velocity, and then we're going to rearrange it to solve for change in velocity, which is delta P over m. Make sure you're in kilograms, okay? Make sure you understand when you get that, it's going to be delta V, the change in velocity, not the final. If you happen to be asked for the final velocity, well, then you're going to have to do what you did on the quiz today to get the final velocity. Add that to the initial velocity. All right? Okay, we had, I believe it was 3 questions for homework, 2 questions on page 462, and then we had question number 9 on our worksheet number 2. Any issues at page 462? Any problems at all with them? With neither of those questions? All right, let's take a look at question number 9 then. Any issues with that question? The answer for that one was 20 Newton seconds for the impulse, 20 Newton seconds, or what else could you have said besides 20 Newton seconds? 20 kilograms meters per second, good. And the change in velocity was 5.0 meters per second. This is one of those perfect examples of do we have to have a right angle triangle to use 1/2 base times height? And of course the answer is no. We can do this as one simple triangle. Although if you did kind of just have one of those brain freezes and forgot and broke it up into 2 right angle triangles, it would still work. You'd still get the right answer. It'd just be twice as much work for you, that's all. Good? All right, I would like to assign now please worksheet, no, sorry, not worksheet, but page 467. I'm checking the correct questions, page 467. Number 1. I don't feel like writing all these down. You can write them down. Number 1, 2, 3, 4, 5, 6, and 7 to 13.
1 to 13.
Got it? Got it? Okay, that's homework for tomorrow. We'll see if we can get you a little bit of time later on in class to work on those. How many would that be now? 13. Those 13 questions a little bit later in class, okay? What I'd like you to do right now is take out your phones and take a look at question number 7, multiple choice question 7. You're going to answer this, please, as multiple choice number 1 on your question responder, okay? Multiple choice number 7, it's recorded as number 1 on your question responder on your phone. All right, guys, good. Question was very well done. Most people got option C, which is the correct answer. Let's go through this just to make sure that we're on the right track as to why, for those of you who did have a little bit of trouble with it. The magnitude of the impulse delivered by the hammer to the pile. We've got a 900 kilogram hammer. It falls a distance of 3.50 meters. Let's call that our displacement. Looking for the impulse. We're going to say impulse is equal to F times T is equal to M times delta V. Okay. Now, pay really close attention to this, okay? Delta V is VF minus VI, right? What's VF here? We got to find it, right? No, we don't. We know what VF is. VF is 0. Okay, when a hammer hits the pile, okay, it stops. Okay, what's VI? That's what we don't know. Understand there's two things going on here. The hammer falls, and then it hits the pile. The final velocity of the hammer falling is the initial velocity as it hits the pile. So we actually have to find the initial velocity as it hits the pile. But we're going to do that by using the same method we've used a bunch of times already. We're going to say VF squared is equal to VI squared plus 2AD for the fall. We're going to get the final speed for the fall, which will become the initial speed for the collision with the pile. Does that make sense? Does that make sense, guys? Now, in the end, because they're asking us for the magnitude of the impulse, you would have gotten the same answer either way. It's not a huge deal, but I just want to make sure that everybody's understanding it properly, even if they did get the right answer. So we're going to say VF is equal to the square root of VI. That's 0, right, because it falls from rest, times 2 or plus 2 times negative 9.81 times the displacement of negative 3.50. What do we get for VF there? .2867 meters per second. The mass here is 900 kilograms times delta V, VF minus VI. Again, VF for the collision with the pile is 0. VI is the same as VF for the fall. So it's going to be 0 minus negative 8.2867 meters per second. Right? 0 minus minus, because, of course, it's falling, so it has a negative velocity, but we're subtracting the negative velocity. When we do the math there, we end up getting 7.46 times 10 to the 3 Newton seconds. They don't have it expressed that way. They have it expressed in kilonewton seconds, but we know that 10 to the 3 is a kilo, so it's going to be 7.46 kilonewtons seconds. All right? I would like you now, please, to take a look at the next one, which is a numeric response question, question number 8. And I would like you to fill that in, please, as numeric response 1 on your phones, please. All right, just about everybody's responded, and the response of just about everybody was 3.55, with the exception of one person who said 3.6. Okay, that one person that said 3.6 clearly knew what they were doing, because they got 3.55 and then they rounded it to 3.6, right? What does it say to round it to here? Record your 3-digit answer, so the answer would be 3.55. Let's go through it here. We know what the impulse is. The impulse was 7.46, I think? 7.46 times 10 to the 3 Newton seconds. We know the time interval here, 2.10 times 10 to the 3, 10 to the negative 3. We're going to find the force by saying delta P is equal to F times T, and rearranging that. F is equal to delta P over T. So 7.46 times 10 to the 3 divided by 2.10 times 10 to the negative 3. This is one of those questions where if you actually get the wrong exponent, you're going to get away with it because you're only asked for the base here. B times 10 to the W. Okay, B times 10 to the W gives me 3.55 times 10 to the 6. Is it? 3.55 times 10 to the 6. But we're going to express it just as 3.55. All right? Make sense, everyone? Good. So we just saw in the video that we just watched, the lethal weapon buckshot video, where Mel Gibson was shot by this shotgun. He was propelled backwards through this glass. The shooter wasn't propelled backwards at all. We just discussed this, and we said that that's not reality. Because, of course, if the guy who's being shot is propelled backwards, he must have got his momentum from the shot. The shot got its momentum from the gun. The gun had a momentum of 0 before it was shot. It had a momentum of 0 after it was shot. Therefore, the guy that was holding the gun should have been propelled backwards as well. In other words, if the shot was propelled forward with a momentum of 50, the guy that was holding the gun should have been propelled backwards with a momentum of 50 as well. Mel Gibson, who was shot, and Gary Busey, who did the shooting, should have been moving at approximately the same speeds after the shot was fired. And they weren't, clearly in that video. The law of conservation of momentum says that momentum's got to stay the same. At least in an isolated system, momentum's got to stay the same. What do we mean by an isolated system? Good, good. No outside forces. No outside forces. In other words, no energy or matter in or out. In an isolated system, a system in which there's no external forces, then the total amount of momentum will always remain the same. Now, we can choose whatever system we want. If we have a system that's not isolated because there's outside forces, let's just make our system bigger. In that bigger system, if we account for all of our forces, then momentum will be conserved every single time. Now, we're going to use this in our analysis of collisions, and I should put in quotation marks, explosions. Okay, the video that you just watched, there was a collision between the shot and Mel Gibson. Okay, that was a clear collision in which momentum should be conserved. But there was another explosion in there as well, for lack of a better term, when the gun was fired. Okay, the gun and the shot were effectively one before the trigger was pulled. Then there was an explosion when the trigger was pulled, and the gun went one way, or the gun should have went one way at least, and the shot should have went the other way. Another example of that explosion would be, quite simply, when you throw a ball. You're standing there with a tennis ball, you throw it, the ball goes forward, you go backward. By the way, why don't you go backward nearly as much as a tennis ball? You should have the same momentum as the tennis ball, so why don't you go backwards as fast as the tennis ball? Jesse? Because your mass is much greater, right? So if you have much more mass, you can still have the same momentum, but not go back nearly as quickly because you're heavier. So anytime we have a collision or an explosion, and by an explosion, we could mean literally an explosion, a bomb exploding, but we could mean something as simple as throwing a tennis ball. Whenever we have one of those two situations, we're going to use this law of conservation of momentum to solve it. And one final little blurb here. We talked about impulse over the last several days. Impulse is a change in momentum. It seems all of a sudden now when we start talking about conservation momentum, we say that the total amount of momentum must remain the same. It seems like all of a sudden I've been lying to you the last few days about impulse, change in momentum. How can we have momentum staying the same, but yet momentum changing at the same time? Well, in the system, momentum is conserved. Momentum stays the same in the entire system, but each individual object within the system experiences a change in momentum. Okay, you fire that gun, the bullet gains momentum. Bullet had zero momentum. Now it's got momentum forward. The gun had no momentum. Now it's got momentum backward. They both gained momentum, but the total momentum remains zero because the momentum of the bullet and the gun are in opposite directions. So the total momentum still remains the same. The momentum of individual objects changes. Now, this is really easy to write mathematically. If we say that momentum is conserved, the total amount of momentum remains the same, then the easiest way to write it is quite simply Pi equals Pf. The initial momentum equals the final momentum. Now, what you've got to do at this point is substitute in expressions for the left side and the right side. Momentum is m times v. So if we happen to have two objects colliding, a car going north and a car going south colliding head-on, then we would say m1 v1i plus m2 v2i, momentum of two objects before the collision. If we had three objects colliding, then it would be plus m3 v3i. If it was only one object, like a gun and a bullet exploding, then we'd just say mvi. We wouldn't say m1 v1i plus m2 v2i. It would only be one term, one object with momentum, so there will only be one mv. Okay, this is kind of this step right here is specific to each problem. Pi equals Pf is valid for all of them. The next step depends on how many objects you have colliding or exploding, what the next step is going to look like. Bottom line is each object is going to have a momentum equal to mv. If you have three of them, then put three mv's in there. m1 v1i plus m2 v2i, and so on. The final momentum, same idea. Right? If you have two objects after the collision has taken place, then it's going to be m1 v1f plus m2 v2f. If you happen to have two objects before and they hit each other and they stick together, okay, like you're shot by a bullet and the bullet stays in your body, then the final momentum will simply be mvf because there's only one object. One term, mv, for each object. Again, pi and pf, always. But then the next step for our substitutions for both pi and pf are going to be different depending upon what problem you're actually solving. Let's solve a problem here on page 477. It says a wooden block attached to a glider has a combined mass of 0.200 kilograms. Both the block and the glider are at rest on a frictionless air track. A dart gun shoots a 0.012 kilogram dart into the block. The block dart system afterwards is 0.78 meters per second to the right. What was the velocity of the dart just before it hit the block? Okay, so this is completely irrelevant over here. What we care about is the collision right here of the dart with the block. The collision takes place, and then the dart embeds itself in the block. It becomes one. So this is going to be initial. This is going to be final. We're going to call this mass right here, the mass of the glider and the wooden block that move off together, we're going to call that m1. We're going to call the dart m2. m2 hits m1. m2 strikes m1 and then embeds itself in it. Something zero. Some velocity is zero. I want you to tell me which velocity that is. First of all, is it v1 or is it v2? Is it the velocity of the dart, the velocity of the block, or is it the velocity of the dart? It's zero. What is it? Good, it's the block. So we're going to call that v1, or we're going to call it v1i or v1f. The velocity of the block before or the velocity of the block after? Let's go before. So it's going to be v1i equals 0. We're looking for the velocity of the dart just before it hits, so we're looking for v2i. We don't know what that is. And the velocity of this block dart system afterwards, right, they stick together, they both move off at the same velocity, we're just going to call that VF. Not V1F, not V2F. It's both of them. They're both going off at that velocity because they're both going off as one object. All right, let's say PI equals PF. Now, we said that next step is going to look different depending upon the problem. That next step has an MV term for each object that we have. How many objects do we have before this collision takes place? What is PI? There's a dart and there's a block. So there's two of them. It's going to be M1 V1I plus M2 V2I. There's an MV term for both objects, the dart and the block. After the collision, how many objects do we have? One. The dart has embedded itself in the block now. The dart and the block have become one. We're going to call that just MVF. There's no point in putting subscripts in there, M1, M2, whatever, because it's one object. Just call it MVF. Now, let's not rearrange here before we plug our numbers in. These questions tend to be easier if you plug your numbers in first. M1 is 0.200 kilograms. V1I is 0. M2 is 0.012 kilograms. V2I is what we're looking for. What's M? What is it? Nope. It's both masses combined. 0.2012. 0.2012. It's both masses, right? The dart is stuck to the block. So the total mass of that one object after the collision is 0.2012 kilograms. 0.212? Yes, it is 0.212. Thank you. And the final velocity of that system is 0.78 meters per second. So now it's just a little bit of math, right? 0.2 times 0 is just 0. In fact, if you recognize that right away, you don't even need to write that term down. Let's multiply 0.212 by 0.78 on the right-hand side. Let's divide that by 0.012. And we find that the final velocity, or the initial velocity, I should say, was 13.78. Or 14 meters per second. Anybody explain to me why the velocity went down so dramatically? The dart after the collision was moving at 0.78. Before it was moving at 14. Why did the velocity go down so dramatically from what it was before the collision took place, Dan? 1 sec. Yeah. The total amount of momentum remained the same, but there's no law that says velocity has to be conserved. Velocity will decrease because the mass increased. Keep the same momentum, more mass, less velocity. All right, your homework is the practice problems on page 477, please. All right, have a good night, everyone.